Swayam Prabha. Digital India. Educated India.
Welcome to the fifth lecture of module 6, in which we shall discuss about the binder based powder bed additive manufacturing. So this is going to be the content for this lecture. We shall first discuss about the binder based powder bed additive manufacturing process working principle and its subsystem. Then we shall discuss in detail about the powder which can be used along with the ink material, the different types of scanning systems, the powder delivery systems, powder recoating systems. Then we shall discuss about three main commercially available machines of different kind for binder based powder bed additive manufacturing system. That is the first one, which is called as 3D printing by Z Corp, and then by X1 the sand printing, and by X1 the metal printing. Then we shall discuss about a very important emerging application of the technology, that is for time delivery drugs. And in the end we shall discuss about the printing process modeling, where we shall discuss about how the droplets can come out of the nozzle and how they behave when they fall onto the powder bed. So this is our classification for the powder based additive manufacturing. Here we have already seen that powder based additive manufacturing can be classified into two categories: powder bed, powder feed. Powder feed we have already discussed. Then in powder bed there could be two categories: one based on the binder used to selectively deposit it on a bed of powder to join the layers together, and another method could be an energy beam is used to melt or sinter the powder particles together in each layer. The energy beam based method could be laser beam or electron beam, and we have also seen that the laser beam based method could be laser sintering or laser melting. So this part we have already discussed, so we are not going to discuss it now. Our focus will be now only on the binder based powder bed additive manufacturing in this lecture. So this is the typical system for binder based powder bed additive manufacturing. So the system is typically consisted of a joining mechanism, which is here a binder based system. A layer of powder is spreaded here, and then from an ink head the appropriate ink falls onto the powder bed, and wherever that ink falls it used to migrate into the powder bed up to a certain height, and then after that those powder particles got binded together due to this ink. These tiny nozzles in the ink head can appropriately deposit the material. So this is the typical joining mechanism which used in the binder based powder bed additive manufacturing. Of course, the part produced by this process may require some post processing as well, because usually if you are going to join the powder particles, those are not really going to join with the binder, but the powders are suspended in a matrix which is of binder. Then of course, in order to achieve better strength in the part which you are producing, you may go for post processing. The post processing steps are very much similar, those we discussed in SLS. So we keep the part first in a furnace and we burn off all the binder from there. The burning off of the binder will leave the cavities or porosities behind. Then in those porosities we can infiltrate a material appropriately so that the density of the part can increase. Finally, the part density, if it is increased, finally the part can be easily produced by infiltration of appropriate material. However, in some cases the post processing may not be required. The particles can properly join together and they will have usually the sufficient strength. So for example, if you have maybe a cement like material and you are dropping the droplets of water onto it, then you know that after a period of time the powder particles of the cement are going to join together and will become hard, and then no further post processing may be required. So as you have seen, it's typically depend on what kind of powder and the ink material you are using in your system. Then there is a scanning system which used to drop the ink over the powder bed. It could be a single nozzle, or it could be multiple nozzles. Also, the droplet those are coming out of the nozzle can be on two types. Either it can be a continuous drop system, or it can be a drop on demand system. Further, the drop on demand system also divided into two categories, whether it is the thermal based or the piezoelectric based. So these are two popular scanning systems, particularly for binder based powder bed additive manufacturing. The next subsystem typically is the powder delivery system. Powder is delivered from a reservoir like you are seeing here, and there could be two possible ways. One is the bottom feeding, another is the top feeding. What you are seeing right now here is the bottom feeding, where there is a reservoir and there is a platform which moves up by the desired layer thickness each time, and the build platform goes down by the desired layer thickness each time after curing the layer. As this downward movement of the build platform will leave a cavity over here on top side, then this delivery system will provide the right amount of this powder to get deposited onto this powder bed. Now to deposit this new layer of powder onto the build platform, a powder recoating system is used. So like I said, in the powder delivery system there could be two possible options. One is bottom feeding like you are seeing here, another could be a hopper on the top, and that can be called as the top feeding system, and right amount of powder falls in front of the recoater or the powder recoating system from top, not from the bottom. Now let us come to the next subsystem, that is the powder recoating system. There could be different options for recoating or depositing this right amount of powder available to the cavity created onto the build plate by utilizing a doctor blade, or by utilizing a counter rotating or forward rotating roller, or maybe a slot feeder. The build atmosphere usually is open environment in the case of binder based powder additive manufacturing system, because usually we do not increase the temperature of the system. Here the part or the green part which you are producing are usually available at the room temperature, and as there is no high temperature or melting involved of the powder particles, then definitely chances of getting these powder particles oxidized, particularly in the case of metal, will be very less. Therefore, these machines doesn't require any control atmosphere and usually have the open atmospheric environment. Of course, the build platform is going to be reusable in this case, and each time after completion of the part is removed and the build platform is reused again. So this video will give you an idea of how this process works. So as you can see in this video, there is a bed of powder and there is a ink head which is depositing the right amount of ink onto the top layer of the bed. Each time it is going to deposit the ink onto the cross section of the slices which I have obtained during the CAPP, and then a new layer of powder is spreaded each time. After repeating the process, the loose powder is removed. Here in this case, the loose powder itself acts as a support material. There is no need to generate any external support in this process. So this is the green state part, and carefully it is removed from the powder bed. Then the loose powder which is acting as a support material into the overhanging zone is carefully removed by the compressed air. After removal of this support material, the post processing can be done. Like here, a coating is provided to provide the strength to the part. Then the whole part is kept into a molten wax and a uniform coating of wax is provided around the part. That will bind the particles from outside as well and will give it a further strength. So, this is the final finished part which is wax coated. Of course, this technology was popularly used as a prototyping technology in the beginning, but nowadays it is possible to create the real life objects also by this technology. It has been found a variety of material can be used, starting from ceramic, metal to polymer, to process through this technology. So, let us discuss about the subsystems in detail. The first one is the powder and ink material. Like I said, it could be ceramic, polymer, metal or even multi-materials as well. This multi-material is the unique quality of this process. As you can see, I am spreading a layer of powder on the bottom and assume that it is having some spherical particles with it. Definitely there will be some voids, and assume that now there is an ink coming from the top and that too is having a material into it which is mixed with the ink itself. Approximately around 30% material can come along with the ink itself. Then appropriately based on the requirement, I can deposit that second material into the required region. As a result, I can vary the composition inside the part appropriately in the desired zone. And as a result, I can make the multi-material component. Like I can have maybe 100% material which is spreaded on the bed at one end, and on the another hand I can have 70% material which was on the bed and 30% material which is coming from the ink as well. Also, there is another benefit that you can use the different colors also along with the ink. Assume that you have 3 ink head with RGB with 3 colors, and appropriate mixture of these droplets falling on a particular location can give you the color to the part. Hence, you can really realize or create the colorful objects by this process. And these colorful objects are not only the having color on the outer periphery but detailed inside as well. The color is reaching into the inside CAD model as well. The next subsystem is the scanning system. Like I said, it could be a single nozzle or it could be a multi-nozzle system. Of course, the multi-nozzle is typically used to have better productivity. The next is the powder delivery system. I have already mentioned it could be either the top feeding or the bottom feeding. And similarly, the last one, which is the powder recoating system, it could be a blade, simple vertical wall which can spread the powder, or it can be a roller, or it can be a slot feeder. So now let us discuss in detail about these subsystems for binder based powder bed additive manufacturing. So the powder and ink. Wide choice of powder and binders are possible for this technology. The binder can be mixed with other material as well, which can come from the top side. Also, like I have already mentioned, different colors and properties material can be dispensed by different print heads. Therefore, the binder based powder bed additive manufacturing can exercise control over local material composition as well onto the layer. The material can be in a liquid carrier or it can be applied as molten matter. The proper placement of droplet can be used to create surface of control texture and to control the interior microstructure of the printed parts. The binder based powder bed additive manufacturing has unique flexibility. It can create part of any geometry almost and out of any material including ceramic, metal, polymer and even multi-materials. Furthermore, it can exercise local control over the material composition, microstructure and surface texture like I have mentioned. The binder based powder bed additive manufacturing is also readily scaled in production rate through the use of multiple nozzles. which has been commercially developed for printing images on paper, which you conventionally use in your 2D printer. So just assume this technology is having nothing but a z-axis in your 2D printer. Again, ink is coming from your cartridge, right? And but the only difference is that now you have a z-axis which each time goes down after one pass of your ink head over the layer. So theoretically, you can just replace that RGB of your color printer, put anything which you want or mix with some other material. Theoretically, it will deposit the material on top of the bed, and then each time you go down, spread layer, go down, spread layer, in your conventional 2D printer can be converted to the 3D printer, which is very much similar to the technology I am describing here, binder based powder bed additive manufacturing. So the typical material used for binder based powder bed additive manufacturing are highlighted here. There are two possibilities. The binding agent can come from the ink which is falling from the top, or the binding agent is available within the material itself which is spreaded onto the bottom on the powder bed. If the binding component is in ink, then you need not to really worry. To make the green part, you can use like any material, because now the binding agent is coming along with the ink itself. And you can either use ceramic as a powder material, you use metal as a powder material, or you use polymer as a powder material. That will not make much difference, because these particles will bind together by the strength of the binder which is coming from the top, and the green parts can be created. So these are the possibilities of powder like ceramic, metal and polymers when binding component is in the ink. And then ink can also be in that case of two types. Either it can be an inorganic ink or it can be an organic ink. The another possibility is the binding component is in the powder. That means your ink is not really carrying any binding material, but binding properties or binding material is available within the powder particle itself. In that case, the ink can be now of two types, and of course based on the ink there will be an appropriate material also, the powder material also corresponding to that. Assume that it is a solvent ink. Then the possible powder particles for that case are like the polylactide and polycarbonate, as you are seeing here. If the ink is like aqueous ink, then the possible powder particles are like starch, cellulose, plaster and ionomer cements. Very much you are familiar with these powder particles. Starch we are very much familiar with, which can be the wheat flour, and if you just spread that flour onto the powder bed and just provide the ink drops which are coming from the top, and this ink is nothing but now the water that is not having any binding agent as such, but when it falls onto the starch, the curing starts and these particles got bind together. We know that. In a similar fashion, the powder particles could be the ionomer cements, or it can be like your plaster of Paris or the cellulose as well. They all give such possibilities of utilizing the aqueous ink along with. So any combination which is highlighted here on this slide is possible for binder based powder bed additive manufacturing system. And now you can appreciate theoretically any material can be processed here to at least produce the green part. Of course, later on some post processing may be required, but from the machine I can get the part. As there is no thermal energy involved here, the loose powder only is sufficient to support the overhang features here. And as there is no possibility of warpage like we discussed in the case of selective laser sintering, here no support will be required to pull this part downward also. Hence theoretically no external support mechanism is required. Therefore, this technology can make any complexity of the part which you want to produce. It will only depend on the minimum layer thickness and the minimum feature size possible onto the machine. Now let us discuss about the scanning systems. Like I have mentioned, there could be two possible scanning systems. One could be the single nozzle, another could be the multiple nozzles. Multiple nozzles you have already seen, like the conventional cartridge of your 2D printer, which used to have the array of small tiny nozzles along the axis. Now in a single go, it just goes from this end to that end and deposit the ink on the paper everywhere at an axis, along an axis where it goes along the another axis. Such printing can save a lot of time. Assume that now you are doing the same thing with single nozzle. Then you have to scan in this direction as well as in this direction. So each time you will go like this in a raster manner. Hence, it will be very time consuming. But think that now if these tiny nozzles are thousands in number and spread it over a right amount of length with the equal spacing or appropriate spacing, then in a single go you just move from this end to this end and it will keep on depositing the material. Let us discuss about the single nozzle in detail, because this multi nozzle is nothing but the array of these single nozzles only. So if we will be able to understand the different types of single nozzle, then it will not be difficult for us to extrapolate our analogy for the multiple nozzles. So there are two possibilities of flow of material through the single nozzle. The first is the continuous drop deposition, or the second could be the drop on demand deposition. Now you can see there is a nozzle here, and this nozzle is providing some droplets with a certain rate. Maybe you can say that the number of drops coming out of this nozzle are like n per second. So in this process, these drops are first given a charge, an electrostatic charge, before entering into the nozzle. As these drops are having some charge now, if I provide appropriate electric field, then these droplets can be attracted toward that. Now to do that, there is a cup here which used to collect some unwanted drops. So drops from the nozzles are coming continuously, they are continuously coming, but the nozzle has reached to a location where you don't want to deposit the material or where you don't want to deposit the binder. In that case, I have to stop the nozzle, but nozzle will not stop in this case because it's continuously providing or injecting the material. So in that case, I have to just get these droplets deflected away from the powder bed in such a way that the required region will not receive any droplet of the ink. So to do that, like I have already mentioned, these ink are charged by the electrostatic. These inks are charged and an electric field is applied here. And if there is an electric field available here, appropriately wherever the droplets are not required, this signal will be given to this electrostatic coil and it will attract these charged particles of the ink drop in a reservoir. Of course, the ink collected here can be reused, but in some cases, as these are the charged ink, may not be reusable and you have to throw it away. So how it works, you can see here the signal diagram. The drop ejection signal is continuous. You can see that it is in pulse and it is continuously going with the same rate. So drops are coming with the same rate out of the nozzle. But you want to block a particular amount of drops which are coming out of the nozzle. So in that case, a signal will be given to the drop deflection system. So this drop deflection system, when it will receive the appropriate signal, it will attract those corresponding drops and it will not allow these drops to go towards the powder bed. So this is a typical continuous drop system. There are some benefits, like there is no inertia involved and you can quickly do the availability or unavailability of the droplets onto the powder bed. However, the major issue here is that the ink which you are collecting into a reservoir either has to be thrown away or it is very difficult to reuse, because if you want to reuse, you have to do some post processing with the ink. It cannot be just directly used. Therefore, nowadays more popularly the drop on demand systems are used. In the drop on demand system, the nozzle doesn't provide the ink continuously. It provides you a drop whenever it is required. It is just not continuously injecting the drops. It has a mechanism which provides you the right amount of material at a particular time only. So, this is how you can see the drop ejection signal for a typical drop on demand based nozzle. As you can see in this zone, no drops are required, hence there is a pulse corresponding to this particular drop and there is a pulse corresponding to this particular drop, and in between there are no pulse given to the nozzle for ejecting the drops. So now let us try to understand the mechanism how these drops are actually coming out of these tiny orifices. There are two possibilities for that. Those are popularly used in the binder based powder additive manufacturing system. One is called as the thermal nozzle and the another is called as the piezoelectric nozzle. In the case of thermal nozzle, there is a resistor. When we provide appropriate voltage difference to this, the temperature of this plate increases. As the temperature of this plate increases, the material or the ink available locally around this tiny plate will increase. As the temperature of this plate will increase, the ink available adjacent to this plate be subjected to high temperature. As the temperature of the ink close to the plate will increase, it will convert to vapor and a bubble will be created. Now, as this bubble has been created now and the volume of the nozzle is fixed, then definitely a same volume of the ink has to be ejected from the orifice. So, due to the pressure applied by this bubble creation here, the ink will be ejected from the nozzle. The second possibility is we use the piezoelectric material. We know the principle of piezoelectric material. When we give appropriate voltage difference to the piezoelectric material, it deflects. Basically, its shape changes. Assume that you have a plate like this, and if you are now giving a voltage difference to it, definitely the shape of the plate will change. And as it is going to bend like this, of course, it will occupy some volume inside the nozzle, and hence the right amount of the volume will ejected in the form of droplets out of the nozzle. So, these are the two most popular mechanisms used for ejecting the droplets out of the drop on demand based system. So, the advantages and disadvantages associated with these two systems are shown here. The thermal head are very cheap, they are not very expensive as compared to the piezoelectric head. Also, the printing speed is quite high in the case of thermal head, while in the case of piezoelectric head, low printing speed is usually achieved. However, in the case of thermal head, there is a risk of exposing the binder to the thermal stress because you are increasing the temperature. And we discussed that in the beginning itself. The foremost advantage of this process should be that the whole thing is happening in a room temperature. Hence, if your ink temperature itself is high, then definitely some thermal stresses are going to be there, and we will lose the foremost advantage of the process of not having any support at all or no warpage, no shrinkage onto the deposited. But as now the ink temperature may rise, there may be a possibility of having thermal stresses onto the part created. While in the case of piezoelectric head, the drops are generated by the deflection of the plate. As the plate deflected, it increases its volume inside the head and the droplets are ejected. Now in that case, definitely no thermal stress will be induced because you are not increasing the temperature of the ink in this case. However, in the case of thermal head, another issue is that non-uniform droplet size may be achieved due to the different size of the bubble created. While in the case of piezoelectric head, always a uniform size of the droplet will be generated. Also, in the case of thermal head, the droplet direction could be not really appropriate and not always vertical. It may even go here and there as well. But in the case of the piezoelectric head, the droplet directionality is very high and it always follows the same path, because each time the change in volume is going to happen in a very similar fashion. So this was about the scanning system. Now let us discuss about the powder delivery system. The bottom feeding we have already seen. It looks something like this, where the powder material is provided from a reservoir and it delivers the right amount of powder towards the powder recoating system from the bottom. While in the case of top feeding system, there are hoppers and the powder materials are available in these hoppers. Then there is a powder bed here where the build platform is also attached. Now the right amount of powder is available for recoater from the top, and then this right amount of powder is spreaded onto the powder bed. So as the material is now delivered to the powder recoating system from the top side, this type of delivery systems are called as the top feeding systems. In a very similar fashion, like we discussed in the case of SLS or SLM, the powder recoating systems are quite similar here as well. Those are the utilization of a blade, simple vertical wall of metal or of ceramic or of silicone or just brush only to spread the layer of powder onto the powder bed. The another possibility is the forward rotating roller or counter rotating rollers. Of course, the forward rotating rollers are bit important in this case, because here there is no melting going to happen. Only the binder will come that will basically keep these particles together. And when you will eliminate this binder or you will burn off this binder, it will leave cavities behind. So if your powder which you are spreading is not really compactly spreaded or deposited onto the powder bed, then there is a possibility that there will be large porosities and it will not, even after the infiltration, you achieve the very high value of the density. While if you have a very compacted layer deposited onto the powder bed, then in that case the ink which is coming from the top will not require to spread onto the very much volume, and also it may be possible now that as less amount is of binding particle are available after burning off, less amount of voids will be there, and hence during the infiltration high density can be achieved. Also, it is important to achieve high pack density of the deposited layer in order to achieve the sufficient green strength of the part. If the part's green strength is very bad, means there is very less amount of binder, then it may break even when you take it out from the machine itself. Therefore, there should be an appropriate optimal value of the pack density which you are spreading. You know that if you are using forward rotating rollers, then they will push the powder material available here downward and increase the pack density of the deposited material onto the powder bed. But if you are using counter rotating rollers, in that case they will pull away the material from the bottom. However, in that case the flowability of the powder will be better, but there will not be any compaction of the powder onto the bed. The next possibility is the slot feeder, which is of simplest kind, where there are powder particles available in the hopper, and when this hopper moves onto the powder bed, which is having a cavity which is created due to the downward motion of this platform, onto that the powder material will get deposited. Now you can see here, if it is moving in this direction, the back wall of the same hopper acts as a doctor blade and spread the right amount of layer onto the powder bed. So these are the different subsystems kept together, and now we can appropriately select the options available here in order to classify these processes further. So our very first process is the Z Corp's 3D printer. So now you please note very important thing, that the name 3D printing was first given by MIT to particular this technology. Then later on, this 3D printing becomes so popular nowadays that everybody calls this technology by 3D printing. And we have seen in our module 1 that why really people call it as 3D printing. So the technology developed by MIT for which is called as 3D printing was capable of utilizing ceramics, polymer, metal or even multi-materials by multiple nozzles. So let me connect it like this. They prefer to do the top feeding of the material and then a slotted feeder is used to spread the powder. So the technology 3D printing which I just mentioned, which uses the subsystems which I just shown you, was developed by MIT and they give this technology name as 3D printing. It is very much similar to SLS which we have discussed, except that the binder liquid is sprayed. The binder liquid is sprayed in the selected region instead of laser. The raw material is powder which can be of ceramic, metal or the polymer. The concept model can be prepared rapidly using a multi-jet, multi-color nozzle. The green part will require sintering inside another furnace as the post-processing of the parts. As the binder is spread through a thin nozzle onto the selected region over a layer of powder, the particles in that region stick together. The remaining powder, which is loose powder, act as a support material. The binder spray makes use of mechanical movement, however, use of multiple jet makes it faster. Explicit supports are not really required and a wide variety of the powder can be used, like I mentioned, starting from metal, polymer or ceramic. A typical system by Z Corp is shown here. So Z Corporation, commonly abbreviated as Z Corp, was founded in December 1994 by Marina H, Walter B and James B and Tim A, based on a technology developed at MIT under the direction of Professor Elias. So the company was sold to Context Holding in August 2005 and was ultimately acquired by 3D Systems on January 3, 2012. So typically the Z printers machine, which is 150 by 250 specification, include the resolution of 300 by 450 DPI, because we are DPI defining because on a sheet the ink is deposited and the resolution of this ink is defined by this. So 300 by 450 dot per inch. So this is the resolution onto the XY plane. Now the vertical resolution is defined by the layer thickness. So minimum features which is possible onto the machine is of size 0.16 inch, that is around 0.4 mm. The vertical build speed was around 0.8 inch per hour, which is around 20 mm per hour. And of course, and the build size is 9.3 by 7.3 by 5 inch, that is around 236 into 185 into 127 mm. The material which they proposed in this particular machine was starch and plaster formations. Later on, of course, many different materials were also able to explore. So these are some of the parts produced on the machines. You can see the colorful objects can be produced because they utilizes the multicolor, multi-nozzle printers. So with this, thank you very much.